Good morning, good afternoon, good evening, depending on where you are calling from or where you are listening to this recorded session. Welcome to Weekly Science Review 10. Weekly Science Review is an event organized by Vetri Labs, focusing on open access journals published in the field of electrochemical science and technology. Today, we have Sabari Rajendran, a second-year graduate student at Kansas State University, to lead the discussion. Over to you, Sabari.
Can you all see my screen now?
Yes.
Good morning or good afternoon. This is Sabari Rajendran, and the topic of the paper that we'll be discussing today is Biomolecule-guided cation regulation for dendrite-free metal anodes. So, as the introduction, batteries are electrochemical devices that can store chemical energy, and it can convert the chemical energy from electrical energy. So, we'll be using the reversible batteries for lots of applications, as we know. Currently, lithium-ion batteries, which has a very huge market in the battery section. So as you can see from this Ragun plot, you can see that fuel cells have a higher specific energy, while batteries has higher specific power than the fuel cells. So the current need is to improve the energy density of batteries by improving the cathode and anode materials. So in this paper, we will be looking at anode materials. So basically, uh, the holy grail of battery anodes is the lithium metal because of its very high gravimetric capacity, as you can see from this plot. Currently, the graphite anodes, they have a very low gravimetric capacity, while the lithium metals have very high gravimetric capacity. Also, in this paper, they have uh, characterized batteries with zinc metal as anodes. So they both exercise high gravimetric capacity for lithium metal anodes, while for zinc metal anodes, they provide a huge volumetric capacity of around 6,000 ampere per liter because of the since zinc is a divalent cation. So, however, it has a lot of challenges when we are using metal anodes. The major problem is the formation of dendrites. So, how the dendrite forms is usually when we have a planar current collector, because of the imperfections on the planar surface, the lithium nucleation or the zinc nucleation will happen at those imperfections. So as we progress, the plating of the metal will happen on those hotspots, leading to formation of dendrites. As the dendritic structure grows in length, so it actually gets aggravated because of the electric field at the dendrite. Because of its very sharp tip, the field will be higher there, so more plating will be happening at that, resulting in aggravated growth of the dendrites. So it can pierce through the separator to create a short and finally a thermal runaway. So it's also a safety concern, as well as poor cycling. It offers only poor cycling ability for the batteries. Another thing that can happen is the formation of dead lithium. So after we plate the lithium metal, when we strip in the following cycle, so the Coulombic efficiency is mostly low, so it's not 100%, so there will be still some lithium left, and the formation of SCI over the lithium so results in dead lithium, which cannot be utilized in the further cycles. So as the cycles go on, the accumulation of this dead lithium results in also the accumulation of new SCI, results in increase in the resistance for the cell, resulting in failure of the battery. So for these two issues, so what the authors of this paper have did is they have used an interlayer material uh, in between the current collector and the separator. So usually without the interlayer, what happens is, so as I said before, lithium dendritic structure form as the metal gets plated. So when the interlayer is there, the concept they have conceived is coating an AGM separator with negatively charged uh, collagen hydrolysate molecules. So with the negatively charged molecules around the AGM separator, what happens is, so as you can see from this figure, so there will be a negative charge on the closely associated with the AGM surface. So what happens is, as the lithium gets plated, so there will be a formation of concentration gradient because of the consumption of lithium ions or the zinc ions. So as they get consumed, there will be an ion depletion close to the metal surface. So in order to have the electron neutrality, the counter ions will get expelled out of this region. So this will result in a decrease in the salt concentration close to the metal surface. So because of this decrease in salt concentration, the bulk electroconductivity will be low there. However, because of this negatively charged ions in the diffusion layer, the what will happen is there will happen a phenomena called surface conduction. So because of that, the oppositely charged, which is the lithium or zinc cations, can be conducted not in the bulk solution but along the surface of the fibers. So along the surface of the negatively charged fibers. So this is called the surface conduction. So because of this surface conduction, even there is a concentration gradient where there is no more metal ions present in the vicinity of the surface. Because of this surface conduction, we can see uh, a current which is higher than the limiting current that is defined by the uh, which is limited by the diffusion. So because of that, it is called the over limiting current because of this surface conduction phenomena. Also, what will happen is it will form a concentration gradient, unlike in diffusion where there will be a gradual concentration gradient. Here it can form a deionization shock. What it means is, so the counter ions, that is the anions present in the solution, they will get expelled out, and there is a drastic change in the concentration. So here there will be a lot of anions, and just next to it there will be no more anions present. So it's just like a shock wave that can propagate in air or water, any other medium. So the difference in the concentration is quite huge, and this shock waves can propagate over time. So because of these two phenomena, what the authors expect, that is, because of these negatively charged charges on the surface can actually control the deposition of lithium metal, which can regulate the deposition of lithium metal on the surface, resulting in the prevention of dendrite growth. Whereas without the interlayer, what can happen is, so this surface conduction will be happening in the opposite direction because of the positively charged AGM separators. So here only the anions will be on the diffusion layer. So while the cations, surface conduction can happen in the opposite direction. So this will have actually can the limiting current will be lesser than the limiting current that can be achieved by the diffusion control process. So what they did is they have actually coated a collagen hydrolysate, which is a protein present in animals and human beings. So collagen is a triple helix biomolecule. So when it is getting hydrolyzed, they will get denatured and they can be cleaved to form a smaller peptides. Mostly they contain glycine, proline, and hydro hydroproline. So these are the major constituents present in the collagen hydrolysate. So this is the weight percent of collagen present in pig skin. So you can see that uh, glycine and proline and hydroproline are the major constituents. So what they did is they took 5% of this collagen hydrolysate and mixed with deionized water and stir it for like 80 degrees centigrade for 2 hours. So this prepares a 5-8% collagen hydrolysate solution. So they just immerse the AGM separator inside the CH solution and for a few seconds and dry it at around 110 degrees centigrade. So based on the difference in mass, they have calculated that the mass loading is around 38 milligram per centimeter square for zinc metal battery, and for lithium metal battery around 43 milligram per centimeter square. Only for the interlayer for lithium metal batteries, they have added like 1 weight % of lithium hydroxide. So in the material characterization, so from this, they have taken a CM image of the CH on top of AGM. So you can see that the porosity of the AGM separator is still retained, and also the CH has been coated quite homogeneously over the fiber surface. From the EDAX mapping, we can see that the nitrogen and the carbon, so these correspond to the peptides which from the peptides which are from the collagen hydrolysate. So the silicon and oxygen are inherent to the AGM separator. So they have also calculated the pore diameter and air permeability to check how it affects after coating, how it affects the performance of AGM separator. So as you can see here, the curly time, which is the air permeability, so how quick a certain amount of volume of air can be passed through the separator or the interlayer. So it is quite similar to the AGM, while and it is superior than the cell guard, which requires a longer time. So and also the pore diameter, as you can see from here, after coating, as is expected, the pore diameter has decreased in the case of CH at AGM. So the authors have probably used an AGM separator which is quite thick. They have used like around 1.3 mm. They might have chosen this instead of cell guard, which is mostly used in lithium ion batteries currently, uh, which have a very low thickness because of these parameters, maybe the air permeability and other parameters. So next, in order also to confirm whether the peptide from the CH are present on the surface of AGM, they took a Raman spectra in that. So they found like the peak at 1654 uh, centimeter, which denotes the amide 1 bond, which is from the CO stretching bond. And there is also two other peaks at around 1440 and 1250, which corresponds to the NH bending and the CN stretching respectively. So also from the FTIR, so from the difference between the glass fiber and the CH at glass fiber interlayer, we can see there is a new peak at around 1650 uh, wave number, which corresponds to the peptide bond from CH. So all other peaks correspond to this silica present in the AGM. So these Raman spectra and FTAR, they and also the EDAX mapping from previous slide, they confirm that the collagen hydrolysate has indeed been coated on the surface of AGM. So next, in order for their hypothesis, so they require a negatively charged surface. They do want a negatively charged surface on top of the AGM. So whether it has been achieved, they did a zeta potential to find out that. So the pH that will for the electrolytes for both lithium metal and zinc metal, zinc metal batteries will have an aqueous solution, and lithium metal batteries will be utilizing an organic electrolyte. So for both of these, the pH will be around like 2 to 6. So at this pH values, they have measured the zeta potential values. As you can see, for the CH coated on AGM, the zeta potential values are negative, indicating that they have a negative surface charge. So these negative surface charge comes from the oxygen functional groups present in the CH backbone, while the AGM, it has a positive surface charge. So yeah, so this also confirms that CH has been coated on top of AGM. Also, it gives insight on the preparation of CH at AGM. Since AGM and collagen hydrolysate are oppositely charged, so when they just come to interact, when they just dip the AGM separator in the 5-8% CH solution, because of the electrostatic interaction, the CH molecules, they get self-assembled because of this electrostatic interaction. So they went ahead to do the electrochemical characterization. So as I said in the initial slide, so in the case of, if you see, in the case of lithium, so they have made a symmetric cell with lithium, AGM, and lithium. Okay, so when they did a linear sweep voltammetry, as you can see from here, so as they increase the voltage, at first the current is increasing, and then it's a you see a plateau. So this is the limiting current because of due to the diffusion of the metal ions, uh, the diffusion limited region. So while in the case of when they used the interlayer CH at AGM, you can see that you don't see a plateau, but you see a linear increase in current. So this is the over limiting current because of the surface conduction phenomena that is happening because of the negatively charged surface on the AGM. So this confirms that the surface conduction phenomena is indeed happening. Uh, so as you can see from the zinc symmetric cells also, a similar behavior is being observed. So this is quite advantageous since a very high current density can be applied for these batteries, and they, they can work without any formation of dendritic growth. So and they also have studied the interaction between lithium ions and the zinc ions, how they interact with the CH molecules. So for this, they did isothermal titration calorimetry. So what they did is they will be adding zinc ions or the lithium ions to a CH solution. So what they have taken only the major peptides that are present, and they titrated it against the zinc ions or lithium ions. And as you can see from here, as they titrate, you can see that there is a negative energy which has been released. So the negative energy tells that heat has been released because of the reaction or the interaction between the peptides and the metal cations. So as you can see, over time it is decreasing, and it is almost around zero. So this tells us that we can find out the molar ratio between for each the tripeptide and the metal cation, how many moles of metal cation it can interact with. So they have did a control experiment with silicon dioxide where you can see there is not much interaction with the peptides, and so not much interaction with the metal ions. Sorry, uh, which we can see clearly because there is no exothermic reaction or endothermic reaction happening. So this tells us that there is interaction between the metal cations and the peptides. So the next step, they did SEM images after doing the chronoamperometry. So they did a chronoamperometry. They just deposit lithium for around 10 minutes at a negative 135 millivolt. So a continuous electrode deposition of lithium with and without the interlayers, and they took the SEM images after that. So as you can see from here, for the zinc for the zinc cells with only AGM, we can see the formation of the inhomogeneous deposition of the zinc metal, while when they have used the interlayer, there is a very uniform deposition. Similar behavior is seen in the case of lithium metal also. So what they did next is, so the batteries, because of the electrode deposition and other reactions, the temperature inside the batteries can actually go up. So also the CH is can be dissolved in aqueous as well as organic electrolytes at a higher temperature. So what they did is, without using any interlayer, they just added the collagen hydrolysate in the electrolyte and see whether it has any impact on the formation of uh, metal deposition. So since from the previous slide we saw that there is interaction between the uh, collagen hydrolysate and the metal ions. So that's what they are trying to see here. So as you can see from here, they did a chronoamperometry for 30 minutes with only AGM without any interlayer, but with the CH added to the electrolyte. You can see that with CH and without CH. So with CH in the electrolyte, they were not, there is indeed inhomogeneous deposition, but the severity of uh, the big chunks of metal is lesser when they didn't have CH in the electrolyte. Similar in the case of lithium. So they, with the CH present in the electrolyte, there is an improvement in the electrode deposition of metals. However, it could not prevent the formation of mossy lithium or dendritic lithium. So it is quite necessary to have an interlayer to regulate the flow of ions to have a homogeneous deposition. So then they made some symmetric cells, both zinc and as well as lithium, to see uh, how it works. So as you can see from here, so they were cycled for 1 milliamp at a rate of 1 milliamps per centimeter square for a capacity of 1 milliamp hour per centimeter square. And as you can see here, the black lines in the case of zinc without the use of an interlayer. So as with the increase in number of cycles, the over potential for metal plating and stripping, it continuously increases, and after certain time, because of the growth of SEI and the increase in resistivity, it increases quite dramatically. While in the case of use of an CH at AGM interlayer, it is quite stable. The both the plating and stripping over potentials, they are quite stable for around like uh, more than 3000 minutes. Similar behavior is seen in the case of lithium symmetric cells as well. in these zoomed in figures, you can clearly see that with the use of interlayers, the stripping plating over potential is very minimal, almost less than half of what can be achieved with the use of AGM separators without any regulation of flow of metal ions. And what they did next is they have actually prepared lab scale full cells. So previous were made with symmetric cells, so both the anode and the cathode were the same metal, while they have went ahead to prepare full cells where the anode would be the metal, either lithium or zinc, while the cathode they have used uh, lithium manganese oxide as the cathode. So all the full cells are limited by the cathode capacity. So in the lab scale level, they have used a cathode capacity of 3.6 milliamp hour per centimeter square, and they have cycled at a rate of 1C. So as you can see from this, so this is a zinc metal battery. So as you can see here, after like 1200 cycles, you can see without the use of CH at AGM interlayer, there is a steady decline in the discharge capacity, while with the use of this interlayer, the discharge capacity does not decline that much. Also, the coulombic efficiency is almost around 100%. They were able to achieve like 99.7% coulombic efficiency. In the case of zinc, they have actually aggravated the testing by increasing the testing temperature to around 60 degrees, because at 60 degrees the collagen hydrolysate may get uh, dissolved into the electrolyte, so the performance may get reduced. Also, at higher temperatures, the side reactions and the reaction of metals with the electrolyte is also will also be higher. So as you can see, with the increased temperature testing, the with the use of interlayer, the discharge capacity, it actually it initially declined to around 50 milliamp hour per gram, and then it shows a stable capacity. While without the use of interlayer, after like 450 cycles, the capacity dropped to around zero, which indicates that there is a short due to either dendrite formation or increase in resistance due to SEI growth. And also the coulombic efficiency is maintained at around 100%. So they have taken the SEM images after 400 cycles at 60 degrees. So you can clearly see the difference between the one with the use of CH at AGM interlayer and without the use of interlayer. So there is homogeneous deposition without any needle shaped metal deposits present when they have used the CH at AGM interlayer, while in the when only AGM is used, you can see bulk chunky lithium metal deposits, zinc metal deposits present. So in the case of lithium, the improvement in the battery performance is quite huge when compared to the zinc metal batteries. So here, after like 300 cycles without the use of interlayer, the discharge capacity is has declined, while with the use of interlayer, it was actually improved to around like 800 cycles, with the capacity decline to around like uh, 80%. So with the SEM images taken here too, you can see distinct difference between the one with the use of CH at AGM interlayer and one without the use of interlayer. So interestingly, they moved ahead to form large scale full cells with a very high loading, because in lab scale level, the electrolyte amount that is being used is quite high, uh, which decreases the energy density of the battery. And also in commercialized batteries, when they move ahead to make commercialized batteries with a very low electrolyte amount to improve the energy density, the performance which is being shown in the half cells or the lab scale level cells may not be reproduced, since the conditions are quite harsh and the batteries won't be perform well enough. So they went ahead to make a 24 milliampere per centimeter square cathode, the very high capacity, and they have used a constrained electrolyte amount of around 10 grams per Ah of capacity. So with this too, you can see that the effect is huge between the use of CH at AGM interlayer and without an interlayer. So the red curve, it shows that after it sustained for around 600 cycles, the capacity declined from around 120 milliampere per gram to more than sustained to around more than 100 milliampere per gram. So here too, in the case of lithium full cells, the effect is quite dramatic. Without the use of interlayer, at around 50 cycles, the discharge capacity is almost zero, while with the use of interlayer, it sustained for more than 600 cycles. So even with this, the energy density with a very high cathode loading and constrained electrolyte amount, the energy density is around 880 watt hour per kilogram for zinc metal batteries, while it is 212 watt hour per kilogram for the lithium metal batteries. Even this is uh, lower because the commercial batteries are around 100 to 250 watt hour per kilogram currently. So since they have used AGM separator and they have used quite thicker separator and two layers of it, the amount of electrolyte they need to use is higher than what is being used commercially. Also, the it is limited by the cathode, and what they have achieved in showing that with the use of interlayer, they were able to uh, improve the cycling of metal batteries from formation of any dendrites or growth of dead lithium or dead metal. They have also went even one more step to produce large scale full cells with the 5Ah, 65Ah, 200Ah batteries for the zinc metal batteries. So for zinc metal batteries, they have used aqueous solution of combination of zinc sulfate and lithium sulfate electrolyte. So for zinc metal batteries alone, they have made large scale full cells of these capacities. So even when they move to commercial level scales, so you can see that the capacity retention they were able to achieve at 1C rate for 5 ampere cells. They were able to achieve more than 500 cycles, the capacity retention of around 90%. While without the use of interlayer, we see a steady decline in capacity with the number of cycles. So for all these cells, which 5 amp hour, 65 amp hour, and 200 amp hour cells, they almost behave quite similarly, and they were able to achieve around like 400 cycles with a capacity retention of 90% with the 200 Ah battery, which is quite amazing. So in conclusion, the authors have reported a general approach to resolve the stability issue which is present in the zinc and lithium metal batteries with quite a practical way and also scalable way of using a cation regulating layer, which is the collagen hydrolysate coated on AGM between the anode and the separator. to suppress the metal dendrite formation. So it can be concluded that efficient dendrite suppression and control can be achieved by guiding the molecules, guiding the cations with the use of charged biomolecules. So benefiting from this effect of surface conduction and deionization shock, a regulated cation flow and deposition can be achieved, and they were able to achieve around like 1200 cycles at 1C rate with a cathode capacity of 3.6 milliampere per centimeter square, uh, with an efficiency of around 99.7% for that, and with even at a higher temperature around 99%, and it is stable for around 600 cycles. Even with a very high capacity, they were able to deliver 600 cycles in both lithium and zinc metal batteries, the coulombic efficiency of 99.7%. So even they went ahead to form commercial level batteries for zinc metal batteries with 100% depth of discharge, and it showed around 30% improvement when compared to the pristine zinc metal batteries. I would like to thank Dr. Chokalingam for giving this great opportunity. Thank you. Questions?
Good one, Sabri. It was very well presented, I felt, and also the paper had like a variety of discussion, starting from a lab scale and how they scale up. So I just have like a small question. So how does this compare with the? Has there been any other peptide that has been used to avoid this dendrite formation, and how does this study compare with the other study?
Uh, there have been studies. People have been using interlayers to. There were actually two approaches to control to have a homogeneous metal deposition. So one using 3D current collectors to reduce the effective local current density, and another like this using an interlayers to regulate the flow of ions. So if you have charged surfaces which can regulate the flow of ions, they should be behaving in a similar fashion.
Okay. Anyone else has any comments, questions?
Yeah, it was an excellent presentation. And I actually tried to read this paper before, and it had a lot of results. And you have done a great job in like summarizing all together and presenting it in a understandable way. And I had one question: like, have they done any like control studies like controlling the thickness of the collagen deposit? Control studies like controlling the AGM. Like, does it have any? Do you think it will have any effect?
Uh, as you can see from the preparation, they just dip the AGM for like a few seconds. So I don't think they have done such control experiments, because what you need is a thin layer of uh, CH, and you need to impose the negative surface charge to the interlayer. So that is their goal, and it has been achieved with very few seconds of interaction between the AGM and the CH solution.
Okay, thank you. And also like with this interlayer separator, so they already use a AGM and they have a interlayer AGM on top of it. So it's a thickness greater than what usually you use it without any interlayer, right? So does that thickness difference would play a role in improving the performance, or like does it have any effect? Like,
Yeah, because AGM itself is quite thicker, and they have used essentially they have used like 2 layers of separator. In the control experiments where they don't use a CH at AGM interlayer, they have actually used 2 layers of AGM separator so that the thickness of the cell is consistent between the control and the experimental one. And also the electrolyte amount, it has been controlled. It is control based on the cathode capacity. So between the control cells and the ones with the interlayer, the result, it is consistent with the thickness as well as the amount of electrolyte, but it does decreases the energy density because of the uh, very high thickness as well as the amount of electrolyte which needs to be worked upon. Yeah.
Okay, so if the separator thickness is decreased, then you say that further the energy density can improve.
Yeah, it can be done, and also it increases the risk of dendrite formation with very low thick separators, very thin separators. The risk of dendrite piercing through the separators that increases.
Okay, yeah, we may have to compromise something. Okay. Yeah, I think, yeah, that's all I have.
Okay. So for next week, in the weekly science review.
Okay, yeah, next week, weekly science review, we'll be discussing about the reaction selectivity of iridium oxide-based hybrid oxide coated on these titanium anodes and their impact on the oxygen evolution and the lead oxide deposition. So with that, I would like to thank you all for listening to this talk. And if you are interested to lead a discussion, please email to info@vetrilabs.com. Thank you.